Hi girls. I didn't get a chance to work a problem with you in class today, and so I thought I would walk you through one of the homework problems I assigned. So this is question 40 in your textbook, and this is a classic projectile motion problem. And the place that you want to start is you want to fill in the information that you're given in the problem, um, and separate the horizontal and the vertical pieces of information. So we know acceleration always for any projectile motion. We know in the horizontal direction it's 0, and in the vertical direction it's 10 meters per second squared on Earth. The velocity, what do we know about the velocity? Here we have Harry flying in a helicopter, and unfortunately he falls out of the helicopter. So that means he's going to, when he falls out of the helicopter, he's going to have the same speed as the helicopter in the horizontal direction, which is 15 meters per second. Since he kind of falls out of the helicopter, it also means that in the vertical direction, his initial velocity is going to be 0. The other thing we know in this problem is we know the time. We know the time for that he will fall is 2 seconds. And that's going to be the same on both the vertical and the horizontal side. And what are we asked to find? How far does he travel horizontally in that 2 seconds? So to answer that question, we're being asked to find the horizontal distance he travels. And the equation that we know for that kind of motion is the horizontal distance is the horizontal velocity times the time. Well, we know the horizontal velocity is 15 meters per second, and we know the time is 2. So dx equals 15 times 2, 15 meters per second, times 2 seconds, which is 30 meters. And that's the answer to the first question. The question continues in number 41, so I'm just going to scroll down. Number 41 says, what are the horizontal and vertical components of Harry's velocity just as he hits the water? So now we're really being asked to find how fast is he going vertically after 2 seconds. So we're being asked to find what is his final velocity in the vertical direction and what is it in the horizontal direction. Well, we know in the horizontal direction that the velocity never changes. There's no acceleration, so his velocity stays constant at 15 meters per second. So if I were to draw how fast he's going on this figure I've got, I know that he's going 15 meters per second this way in the horizontal direction, and we need to figure out how far is he going vertically. Well, if he accelerates at 10 meters per second every second and he falls for 2 seconds, how can I figure out how fast he's gone? How fast is he going right before he lands? The equation that I need to use for that, and I'll just put an arrow up here because I've run out of space, V final in the y direction, remember, equals gt. So that's 10 meters per second squared. Oops, my pen's getting a little off. Times 2 seconds. So he's going to be going 20 meters per second. So in the vertical direction, he's going 20 meters per second. So that's the answer to part A of that question. Now I have to show that Harry hits the water at a speed of 25 meters per second. So what I'm really being asked to find is what is his resultant velocity. So remember, to find the resultant, I have to kind of use the parallelogram method, and I need to figure out what is the resultant velocity. How fast is he going, combining the horizontal and the vertical motion? And to do that, I'm going to use the Pythagorean theorem like we've been practicing in class. So his velocity overall then is going to be the square root of 15 squared plus 20 squared, and that's equal to, if you take the square root of that, I think you're going to find that it is 28 meters per second. That's how you do a projectile motion problem. You separate the motion into its horizontal and vertical parts, and then you solve for the things that you're looking for. I have also worked out another problem in your packet, and I'll post that solution online so you can see another problem to help you practice. Thanks and have a good day.